Hello students, welcome to BTech first year physics course. In the last lecture, I have discussed solutions of various types of problems related to line integrals, gradient of scalar potential and conservative property of any vector field. Right? Now today, I shall discuss about the concept of surface integral. How one can define surface integral and where we can apply this to find out any physical quantity. Okay, so let's start. Suppose S is a two-sided surface. Let's consider the upper side as the positive side. And if S is a closed surface, then this will be taken as the outer surface. Okay, then a unit normal n cap to any point on this positive side of this surface is called positive or outward drawn unit normal. And ds vector is an elemental area on this surface at that point where the unit normal n cap is drawn. Then we can write the area ds vector as n cap ds. Now suppose we have a vector field V in this region which crosses the surface. Here these lines are pictorial representation of that vector field. Okay. Now the number of field lines which passes through this elemental surface area ds can be represented as V vector dot ds vector, and total number of field lines which passes through the total surface area S is measured as open surface integral V dot ds over the total surface area S, and this is called flux of vector field over any surface. So this is one form of open surface integral of vectors. Okay. Now other forms of open surface integrals are like this: surface integral V cross ds and surface integral phi ds, where phi is a scalar function or scalar potential. Now if the surface is closed which encloses a finite volume, then the integral over closed surface can be represented either by this notation or sometimes like this. Okay, and when you see this type of integration, it is also called double integral. Okay, now suppose the surface is very much arbitrary or the direction of normal on the surface varies at each point. For example, a cylindrical surface or hemispherical surface on which the direction of normal varies at each and every point, right? In that case, it becomes difficult to integrate any vector field over those surfaces. Okay. Now to simplify the problem, we can take projection of the surface S on any known plane of Cartesian coordinate, either on xy plane or yz plane or xz plane. So here, for example, we have taken projection of the elemental surface area ds on xy plane, and that is dA, and R is the projected region of total surface S on xy plane. Now there is a particular relation between ds and dA, and that is dA equals to ds cos alpha. Here alpha is the angle between the normal direction of xy plane, which is k, and n cap, right? And we get ds equal dA by mod of n cap dot k cap, then dx dy divided by mod of n cap dot k cap. Okay. Now putting this form in the expression of open surface integral of vector field, we get this form. Now here n cap is unknown to us. We have to find out n cap. Now to do that, the equation of the surface has to be known. And you know that can be represented by any scalar surface, right? Let's say that is phi and it is function of x, y and z. Then any arbitrary equation of scalar surface can be written like this, right? And the unit normal on that surface can be quantified as gradient of phi divided by mod of gradient of phi, magnitude of gradient of phi. Okay. Then if we put the expression of n cap here in this integral, then we get the general form of surface integral. Now let's see some physical examples of surface integrals. So the total charge on a surface can be written like this. Here sigma is the surface charge density. Then total electric flux through any closed surface is actually the measure of charge enclosed by the surface, and that is closed surface integration E dot ds equals to Q enclosed divided by free space permittivity. This is called integral form of Gauss's law, right? That you know. Next example is net flux of fluid crossing any surface can be written like this. Here rho is the mass density and v is the velocity of the fluid. Another example is electromagnetic flux of energy which flows out of a given volume V bounded by a closed surface S, and it can be represented by this equation. Here this E cross H is called Poynting's vector, and this will be discussed in the lecture series of electromagnetic theory, not here. Okay. Then another example of surface integral is solid angle. So what is solid angle? It is a three-dimensional analog of a angle, right? So you know the two-dimensional angle. Solid angle is three-dimensional analog of that angle. Okay. And the symbol is omega. Here d omega is the solid angle formed by this elemental surface area ds, and total solid angle formed by this hemispherical surface at the center is surface integral r vector dot ds by r cube. Okay. So these are the concept and example of surface integral. Now today we stop here. In the next class I shall discuss few important problems and their solution related to this surface integral, and you will understand how to do surface integration. Okay. So thank you for listening this lecture. See you in the next class.